What we're going to do is, I reminded you about the midterm exam coming up Monday next week and bring in homework 1 through 11. What I want to do today is I want to clarify a couple points that I made with you from the last class session, and then I want to make sure we work another problem or two out using work energy. Work and change in equals change in kinetic energy. And then have a little bit introduction and maybe get started doing some problems with a variation on this equation. It's the same concept. It'll actually be easier for you to solve the problems, the work energy type of problems, once we get this introduced. And this is the way I usually work them. So with that in mind, what I'd like to do is to clarify something from class. From the last class session, and early in chapter 3 the book discusses this concept. What I want to show you is right down here on the bottom of this page, and I'll go ahead and bring this in so we can see it. When I showed you the kinetic energy, or excuse me, the energy or the work done associated with moving a mass, I actually presented it from the perspective of potential energy. And if you look in your notes, I believe I had a positive mg and h2 minus h1 or y2 minus y1, if you have notes on that. Anybody take a look at that? Yeah, I had a positive, didn't I? Yeah. And the way I described it to you, was we have a mass that has a certain weight mg. And what I was telling you in class last session was that I was looking at the work done by pushing that mass from some altitude y1 up to some higher altitude y2 or h2, h1 or h2. And so that would have been positive work because that work would have been done, or that force would have been in the same direction as that. But I want you to look at the wording here for, in this section of the book, the way they're describing the work done. It's the work done by the weight, mg, of the body as the body is displaced from an arbitrary altitude y1 to a final altitude y2. So they've laid it out here in its vector form for the dot product, and I'd like you to look carefully at that based on that wording. The work done by the weight mg. So the weight mg is directed downward, so they assign a negative mgj to that vector force, and they dot that with a motion in x and y. Then the dot product of orthogonal vectors disappears. As you know, j dot I is 0. Everybody comfortable with that? And you're only going to be dealing with the scalar product of minus mg and dy, which is shown right here. And so the work done, make sure you're clear on that. The work done by the weight as it is displaced actually turns out to be negative if y2 is greater than y1. So it's the work done by the weight. Now I'll make sure we work a problem today from that perspective.
If the force is in the direction of motion, or if the force is in the direction of displacement, then the work done by that force is positive.
That's correct, but keep in mind what we're doing here is, I had it backwards the way I was explaining it. I was actually talking more about the stored potential. So just all you have to do is draw your free body diagram, and you've got your mg pointing clearly downward. The work done by that force downward as the body is lifted upward is negative. Albert?
So before we were trying to find out the work done by saying, okay, the force is in a downward direction, so we want to know what the vertical motion was. Now we're using a dot product, so that takes care of all of the angle stuff that might be going on. Like if it's not entirely in the direction of the force, that automatically takes care of that.
Yes. Yeah. And actually that was all done. That was all explained correctly in the last class session. The dot product is by definition the work done. Because what it is, and you can look back at the old notes or look at the DVD from the last session, is it's the component of the force in the direction of the displacement times that displacement. And that, or you can think of it another way, you can say the entire force, and it's the component of the displacement in the direction of that force times the entire force. So it can be the component of the displacement times the force, or it can be the component of the force times the displacement. And they're either going to be positive signed or negative signed depending on the cosine of the angle between those two vectors. Let me clarify. That's an important concept. As we had the other day, we had a vector like this. And let's say our displacement is this. Okay? And so if I want this to be my displacement, then there's an angle between these two vectors that the book is denoted as alpha. So the work done there is F dot, in this case D, F dot D, and two ways of doing the mathematics on that. Here's vector D. Say that's vector F. Here's angle alpha. I can take the component of F that's in the direction of the displacement, which is going to be a scalar F cosine alpha, and I can multiply that by the magnitude of D. So that dot product could be described as F dot D can be described as the magnitude F cosine alpha times the magnitude of D. So this is the amount of the force that's in the direction of D. The other way of describing that, here's F, here's D, is I can take the amount of, let me change the length here so we don't get confused. I can take the amount of D that's in the direction of F, that's D cosine alpha, and the dot product is still going to be the same. It'll still be the same. It'll be D cosine alpha times the magnitude of F, all of the force. Okay? Let's work another problem out using that concept. Oh, and there's another point I wanted to clarify with you as well before we go forward there, is I may have assigned one problem dealing with power. And in the book, power is a definition. It's the time rate of doing work. The time rate of doing work. So power It's a scalar quantity. It's F dot dr, and it's the rate at which that's occurring. So oftentimes mathematically, if you have a particle in motion, you can take the active forces and dot them with the velocity. And that's the power that that particle has at that instant in its motion. That's the power that the particle has at that instant in its motion. Now the units of this are going to be, in the international system, newtons times meters per second. So it's Newton meters per second or it could be pounds of force times feet per second, which would be foot-pounds per second. And our book does a nice job of laying this out for us right here on the same page. Is a Newton meter is a joule of energy. So the power is a joule per second, abbreviated capital J per second. Or we have foot-pounds per second. Now a joule per second is defined as being 1 watt. And then we have foot-pounds per second and a horsepower, which is this archaic system that we're still living with in this country, which is 550 foot-pounds per second. And I never remember that factor. I always have to just look it up when I need it. Okay, so when you need it, just look it up. And being aware, probably most importantly, of the international system of measurement. Joules being Newton meters, which is are the units of work, and it's the time rate of doing work, so it's joules per second then. Okay. One other point that I think was touched on in this section, it's right down here on the same page, is efficiency. Let me hit the autofocus, see if that picks it up there. That's a little better. So what the efficiency is power output divided by power input. Power out divided by power in. Now, in an idealized situation, which would be 100% efficient, both the power in would equal the power out. But nothing is 100% efficient. So you're always going to get a percentage reading coming out of this, something less than 1. Okay? There are several types of efficiency in engineering. One is, and we oftentimes use just a small letter E to represent this, mechanical efficiencies, electrical efficiencies. There are thermal efficiencies. And those are the most common ones. And I believe they've actually shown you that what happens if you have the mix, you have let's say you have all these components going on. You have some thermal energy embodied, say, in a fuel, and then that fuel is burned and gives off heat. So there's some loss to the universe in that burning process, And so there's something less than 1 or less than 100% efficiency thermally. You may have used some of that thermal energy then to generate some electricity, and there's losses electrically, and there's losses mechanically if you have, say, a power takeoff occurring. Then the effective efficiency is going to be equal to the products of these various elements of efficiency. Okay? Oregon Institute of Technology does a really great job with having their students do things. You learn the theory, like we're learning here, and then they have lab components with absolutely everything. You get your hands dirty a lot more at Oregon Institute of Technology, actually building things and monitoring things for their performance than you do at a university level education. Although I think Oregon State actually does quite a good job, and most of the major engineering schools nowadays do a good job, but not as much getting your hands into it as OIT does. I remember being down there years ago, and they had a big pretty powerful diesel engine, and they had thermal blankets around it with all kinds of thermometers, instrumented thermometers on it. They had power takeoffs from drive shafts coming off of it, and they were able to instrument that to measure the mechanical efficiency coming out. And then they also, well, I think they were even generating some electricity coming off of that shaft, and they were able to look at the overall efficiency because they knew what the energy was in the embodied fuel that was powering that motor. So it's pretty neat, and the students actually got to see this stuff for real instead of just cranking out the mathematics on it.